So this is a very interesting mechanics problem, which involves a few principles that work in somewhat unexpected ways, and I'm gonna go through it, and then at the end, once we get the final form of our answer, I will also show it to you in practice. You'll see what I mean by that when we get there. So let's read the question and let's try to make sense of it. Now, this is the kind of question that would probably be given to you in an Olympiad if you're expected to participate in an Olympiad type competition. Then you might get something along those lines if you're doing mechanics. And if you would like anything else that you want to go over, let me know in the comments. So we've got a wedge, and the wedge is made of a very light material, which is key here. So this object here with this shape, this is made of a light material, which obviously it means that the mass is negligible, and it has two frictionless inclined planes. So there's no friction, and you'll see there's no friction with the wedge, there's no friction with the floor, with this plane as well. So there's no friction at all. And then we have a block of mass m, which is placed at the bottom of the inclined planes, and another block which has a mass capital M, which is, for now, it's held motionless at the top of the inclined plane on the right. And what we have to find is the range of values of m. So we have to find m as a function of big M, as well as the angle of inclination theta, so that when the upper block is released, so what we want is that when we release this block small m is going to start sliding up the wedge. So that's what we're gonna look for. So why would this happen in the first place? So the reason for that is essentially, as m is going to be sliding, it will exert, as you'll see, it will exert a force, a normal force on this wedge, and that force is going to accelerate the wedge towards the right. So the wedge is going to have an acceleration, and if this acceleration is fast enough, then at the moment there is some sort of reaction force like this, which is acting on the object small m. So if that acceleration is big enough, that reaction force R will vanish, and we're gonna understand in more detail why that's the case as we start doing the problem. But as usual, the way we do anything like that is by drawing a free body diagram of each object that's important. So let's start with big M, and we have this wedge which doesn't have a mass, so I guess we don't have to worry about naming the mass of the wedge in any way. So anyway, we've got object big M, which has a weight which is acting downwards, which is mg, and then we're going to decompose this into the normal and the tangential components. So we've got this component here, which is mg cos theta, and we also have this component right here, which is of course mg sine theta, and on top of that we also have this angle, which is theta. And then we don't have friction, but we do have this normal reaction force like this. Now you might be tempted to say that mg cos theta is equal to n, but in this case this is not true, so we're going to remove it. The reason this is not true is because the plane itself is not stationary. It's most likely going to accelerate. So if there is any acceleration in this way or in this way, then those two are not equal to each other. So we're going to cross it. Yeah. But we can still write the equations of motion as usual, so let's do that. And we're going to do it in the tangential direction and then in the normal direction. So in the tangential direction, we have, well, let's pick our axis first of all. So I'm going to say that this is going to be my positive direction, which I'm going to call x, and this is going to be also my positive direction, which I'm going to call y. So I'm making my positive axis to go down the incline and perpendicular to the incline going into it. So in this case, we have mg, big mg sine theta. There's no other force in the x direction, so this is just equal to m times a, I'm going to call it a1. This is the tangential component of the acceleration of m, and we also have mg cos theta, which is positive because it's going in our positive y direction, how we defined it, minus n, and this is equal to big M times a1n, and I'm going to call this a1t actually, just to differentiate between the two. One is tangential, one is normal. Okay, now what we have next is, I'm not going to do the free body diagram of small m first, or yet I should say. First we should look at the wedge constraint in terms of the acceleration, because there is a wedge constraint that we have to take into account. So from previous videos we've looked at how to deal with constraints where strings are involved, but sometimes you have planes like this double incline which has which is accelerating. So there is a constraint here that we have to understand, and this is how the constraint works. So I'm going to draw the incline like this again. This is sort of, it's not a free body diagram, by the way. This is more of a, I guess, a kinematic diagram, we could call it. So what I'm doing here is I'm going to draw the acceleration of the wedge. So clearly we know that the wedge is going to accelerate to the right, but it doesn't actually matter if it's going to the right or going to the left. For this problem, it will go to the right, and it's constrained to move along the horizontal direction. So the acceleration of the wedge, I'm gonna draw it here like this, it's 100% going to act like this, and I'm going to call this A, just A, not A1, A2, just A. So this is the acceleration of the wedge. Now the next thing to keep in mind is that both objects, but I'm talking about object M for now. So object M is not detaching from the wedge. It stays on it. So in a sense, it kind of moves with the wedge, but what this means mathematically is the following. So if we look at this acceleration and if we try to kind of decompose it, so we're gonna decompose it into, again, tangential and normal. So we have this here. Oh, and by the way, we know the angle is theta, so this arrow here and this angle is theta too. So this is a cos theta, and this right here is going to be a sine theta. And here's the wedge constraint. So this object will accelerate in some way, but no matter how it accelerates, no matter what the acceleration of m is, the acceleration component perpendicular to the plane will be the same as a sine theta. So what I'm saying is, if this object is going to accelerate like this, for example, we have no idea what the tangential component is going to be from this kinematic relationship. Like, this kinematic constraint doesn't tell us anything about the tangential components, but it tells us everything we need to know about the normal components. So if this is let's call it A1 and this is A1n, A1n and A sine theta have to be equal to each other, And if you think about it for a bit, this has to make sense, because if the plane moves 1 centimeter in a direction perpendicular to itself, then the object must follow along and must move 1 centimeter as well. So I can kind of draw it here. So let's say this was the original position of the objects, of the plane and of M. And then if this plane moved like this, then this object has to also move. So we don't know how it moves tangentially, but we know that it has to stay on the plane at all times. So it can't jump away from the plane, because we know that's not happening in the problem, and it's not like melting in the plane either. That wouldn't really make sense. It's not the kind of problem that we're interested to solve. So if the plane moves however much, 1 centimeter in a direction perpendicular to itself, then this object also moves 1 centimeter in a direction perpendicular to itself. So however the incline moves perpendicular to itself, the acceleration or the velocity or the displacement of the block has to follow that constraint to the ladder. So this must be true. So yeah, this is something that we're going to use to understand some things about this problem, but hopefully it's clear. So what I'm going to do is I'm going to take this and I'm going to replace A1n with A sine theta, like this. So the acceleration of the plane perpendicular to itself is the same as the acceleration of the block perpendicular to the plane. And it's going to be the same with the second object as well. Okay, so this equation is not really going to help us too much. I mean, we can find what A1t is, which is g sine theta, but again, this is not going to be very helpful, as you'll see in a bit. But what we can say is this equation, I'm going to rewrite it on the next page. So we have mg cos theta minus n. This is equal to ma sine theta. And I'm going to call this, for now, I'm going to call this equation 1. And then let's look at small m, and let's see what's the deal with small m now. So small m is sitting on an incline which has the same inclination, but it has, if you want, a negative slope. And we're interested in the scenario where m starts climbing upwards. So let's understand when that would happen. So if small m starts climbing upwards, so I'm going to draw it like this. When it's resting, there has to be some kind of reaction force holding it, because there's no friction, so that it has to be held by this reaction like this. So if it's climbing up the incline, then this force represented by the red arrow, that can't exist anymore because it's climbing. So the only forces that are acting on the small block are the weight. So this is small mg now with the corresponding components. So I have, as usual, I have this, which is mg cos theta, this is theta, and this is mg sine theta. Mg sine theta, and I also know there's a normal reaction force that I'm just going to call this one n prime. And as before, n prime is not going to be equal to mg cos theta for the same reason. So this surface, the slope, and the wedge is going to be accelerating, so this can't actually be true. So we're going to keep this in mind. And what we can say is that n prime, so in this case, let's pick our coordinate system. So what I'll say, I think, so I know this wedge is going to accelerate like this. So for convenience, purely for convenience, but you don't have to do it this way if if you don't like. You can choose any other coordinate system direction that you want. So I'm going to make this positive now, again for convenience, and this is going to be also positive like that. So along the x direction, we have mg sine theta is going to be equal to mat2, and then along the y direction, I'm going to have n prime minus mg cos theta is equal to man2. Okay, so now we have to apply the same kinematic constraint as before, which is going to be identical basically. So in this case, we have this slope accelerating also to the right, and we're going to look at the acceleration components, trying to make it as accurate as possible. So this is going to be an, and this is going to be at. But now we have to think which one is sine, which one is cosine. So if this angle is theta, then what we can say is that, let's think about it. So this is perpendicular to the plane, and this, I would say this angle here, or rather this angle here, is theta. Yeah, I think that's about right. So what that gives us is that the normal component is going to be a sine theta, which is the same as what we had for object 1, if you remember. So we have a sine theta was the normal component, so it makes sense to be the same in this case, and this is a cos theta. Okay. And that object, which is, you know, sitting on the plane, well, it's not sitting at this point, it's accelerating. It will have some acceleration. We don't know anything about the relationship between A and the tangential acceleration, but we sure know that the acceleration of this perpendicular to the plane, which that's what we call an2, this has to be equal to a sine theta. So as usual, I'm gonna remove this and I'm gonna call this a sine theta. Okay, and I think we're done with equation 2. And there's another equation we can write regarding the wedge itself, which is going to be an interesting relationship that you're gonna notice in a second between the forces that are acting. So if this is the wedge, then we have theta, and let's think what forces are acting on it. Well, clearly we have n. Let's make this a straight line. So we have n, which is acting from the first object like this, and we have n prime, which is acting from the second object like this, and we know this is theta, we know this is also theta, and we know this object is accelerating like that. So we can, you know, we can draw, we can write the equation of motion. Oh, and by the way, this one should technically have another normal reaction force here, but we're just going to ignore it because it doesn't really do anything. We're only going to look at the horizontal equation of motion. So what we have, therefore, let's move this a bit to a different page. So what we have in this case is that n sine theta minus n prime sine theta. So those are the, you know, those are the horizontal components like this and like this. Those are equal to the mass of the wedge multiplied by the acceleration. The mass of the wedge is 0, so this is 0, which means that n is going to be equal to n prime, which is a very interesting conclusion. So it doesn't actually matter what the masses are for the objects, because no matter what the masses are, then the normal reaction forces are going to be equal, or in other words, the wedge is going to think, quote unquote, is going to think that the two objects that are sitting on it have the same weight, because the normal reaction forces, those are the apparent weights of the objects, and the wedge is going to think that both objects are having the same mass, which is clearly not true because we haven't constrained big M and small m in any way. They can be anything at this point. But anyway, so this is therefore our third equation, and now let's try to solve this and see what happens. So the first one was mg cos theta, I think minus n, and this is equal to ma sine theta, and the other one is n prime, which is just n, so I'm talking about this one, minus small mg cos theta, and this is equal to ma sine theta. So this used to be n prime, but I use this relationship and it's no longer n prime. Okay, now I don't really care about n, to be fair, so I can just add up those equations and n will cancel. And what we get is mg cos theta minus mg cos theta is equal to, so I have ma sine theta plus small ma sine theta. Okay, now we can do a bit of rearranging, and we get that g cos theta times m minus m is equal to, so this is going to be a sine theta times m plus m, and we get therefore that the acceleration is going to be equal to g, let's say this is going to be equal to g cos theta over sine theta multiplied by m minus m over m plus m, like this. And then we can say that the acceleration is g divided by tan theta, and then we have m minus m over m plus m. Yes. So the question is asking us to find the range of values of m in terms of big M, so that when the upper block is released, the lower block starts sliding up the wedge. So what we should look at in this case is actually the acceleration of the second object, small m. So we know that, well, this is the formula for the acceleration of the wedge. Now the acceleration of, or I should rather say the tangential acceleration of the second block. So the tangential acceleration of the second block, we can get it from here, like this. So we have that mg sine theta is equal to mat2. Therefore, the acceleration, the tangential acceleration of the second block is going to be g sine theta. And this acceleration is going to be down the incline, which is going to be relevant in a second. So let's think what happens to this second object. So if this object, this small m, is accelerating down the incline with an acceleration which is g sine theta, the only way in which it's going to start climbing up the wedge is if the wedge itself will have a tangential acceleration, or will have an acceleration component in the tangential direction greater than g sine theta, essentially. So in other words, this small m will never be able to reach back to the bottom of the slope, because the slope itself is moving faster than it. So this would therefore be at, right? And we know the acceleration of the incline is equal to a, and we know the normal component is a multiplied by sine. So this is a sine theta, which means that this here is going to be a cosine of theta. So what we need is actually that this tangential component, this a cosine of theta, we need this to be greater than g sine theta. So this is going to be the condition that that small object m is going to climb up the slope instead. So we can actually solve this inequality and see what we get. So I'm going to replace a by this, and we get g over tan theta, and then we have this mass ratio here, which is this is going to be greater than g sine theta. The g's cancel out, and we get that m minus m over m plus m is going to be greater than sine theta times tan theta, or sine squared theta over cosine of theta. And now I just realized that there should be a cosine here as well. So when I divide both sides, this is going to be cosine squared, and this is going to be tan squared. So we can now write that m minus m over m plus m has to be greater than tan squared of theta. And then we can just rearrange and see what we get in terms of small m. So this is going to give us that m minus m is bigger than m plus m tan squared theta. And we can rearrange this, and if we do so, we're going to get small m times 1 plus tan squared theta is less than m1 minus tan squared theta, which gives us that small m over big M is less than 1 minus tan squared theta over 1 plus tan squared theta. So we can actually do a bit of trick here. So we can swap the tan with sine over cosine, and we're going to get this. It's going to be 1 plus sine squared over cosine squared, and we're going to apply even more trick to simplify this as much as possible. So on the bottom, we're going to have cosine squared plus sine squared, which is 1. And then this is divided by cosine squared, which cancels with this one. This here is 1, and this here is cosine of 2 theta. So what we get in the end is that small m over big M has to be less than cosine of 2 theta. So in other words, if this is true, M, the second object, the small one, will climb up the incline. So this is the relationship that will always work. Now keep in mind, this is only true if there is no friction, and most importantly, if the wedge has 0 mass. So let's try to do a simulation. I'm going to use a software in a second, but to do the simulation, we're going to have to use a specific value of theta. So let's say, for example, that theta is 30 degrees. You know, it's a nice angle, which means that cosine of 2 theta is the same as cosine of 60 degrees, which is a half. So for this object M to slide up the incline, we must have that, you know, this relationship is true, which in this case, this is going to be a half. So in other words, we're looking, or we're saying that M should slide if its mass is less than half of the mass of big M. So, for example, if big M is 4 kilograms, then for this to happen, small m has to be less than 2 kilograms. Now, would this work in reality? Well, we can't actually simulate this in reality because, there's all sorts of other unwanted effects, but we can use the second best thing, which is a simulation. So I've got here a very convenient software, which is the one you see, well, you should see it right here, I think. And I have got exactly what we have in the problem. So we have the wedge. Well, it's not really a wedge, but it works like a wedge. And those are, those three objects that I highlighted, those are joined together, so they move as one unit. And their masses are not really zero, but they're very small. If you look, this is 10 to the power 4, the order of 10 to the power 4 kilograms. This one is also very small, and well, so is this one. So this one is about 0.7 grams, this is 0.8 grams or 0.9 grams, and this is 0.5 grams. So in total we have somewhere, I would say, around 2 grams maybe, which is good enough. I would make this density or the mass even lower, but that would result in some very weird behavior, so I'm just gonna leave it like this. But let's focus on, oh, and there's no friction either. So if you look at the friction, this is the friction coefficient basically. So there's no friction associated to any surface basically. And the objects, so I have one object here which has a mass of 4 kilograms, and I have a small object which for now has a mass of 4 kilograms. So according to all this theoretical analysis that I did, the moment I press play, so the moment I run the simulation, and I'm doing this at a simulation speed of 0.3 for now, just to have time to absorb everything that's happening. So if I run this object should slide, but this object should stay here. So let's see if that's the case. And as you can see, that's exactly what happened. So I'm gonna pause a couple of times. So as the red object goes down, see this wooden block just stays here and doesn't really go anywhere. Okay. So this is in line with what we have here. So we know that according to our analysis, sliding of the small block should only happen if its mass becomes less than what we have here, if it becomes less than 2 kilograms. So let's change the mass to something else. So let's not make it 2 straight away, let's make it 3. So now we have this block which has a mass of 3 and the big block has a mass of 4. So we've reduced the mass, and if we run it, as you can see, it's still not going anywhere. So we'll try to reduce it further. So let's go to, now we're gonna do 2.5. Okay, let's do 2.5, and then we'll go to 2. So if I do 2.5, again, it's just sitting and not going anywhere. So let's make this mass, let's make it exactly 2. Or 2.1 actually, for now. So if I make it 2.1, according to our analysis, it should still not be going anywhere. And as you can see, it's not going anywhere. And if I make it 2, so 2 is the limiting case, and we'll see what happens if we make it 2. So if I run it, it's still not going anywhere. But remember, the masses of the wedge, of the wedges of those other surfaces, of the other objects actually are not actually zero, and 2 is a limiting case anyway. So the theory says if I reduce the mass of this small object just by a tiny bit, it should start moving. So let's make it 1.95 kilograms. And I'm gonna reduce the simulation speed. I'm gonna make it 0.2. And let's run this. So as you can see, and now it's pretty clear that the small objects slowly started going up the incline. And it's going slowly because, you know, its mass is on the, it's very close to the boundary of 2 kilograms. And remember, so it has a mass of 195 and the mass of this one is 4. So I've crossed the boundary and now it's behaving exactly like what we analyzed. So if I reduce it further, it should theoretically accelerate up the incline even more. So let's do it, let's do 1.8. If I do 1.8, it's going to start going up the incline more. Now we've looked at why this happens. So the reason it goes up the incline is because, well, it's not actually going up the incline as seen from a stationary observer. The block is actually sliding down the incline, but the incline is kind of sliding down itself with an acceleration higher than that of the block. And it looks like the block is going up as a result of that. So let's try something much smaller. Let's do 0.5. So if it's 0.5, I think this is going to be very dramatic change. Yeah, as you can see, we're going to ignore this. So the more you reduce the mass of the small block, or the not necessarily the mass of the small block that has to be reduced, it's the ratio that matters. So I can make this one 2 and make this one 10. And if I run it, you're going to see that this one will accelerate up the incline very fast. So yeah. So this was essentially the question. I used a visual tool. So that tool is called, it's kind of like a physics sandbox. It's called Algodo, which is free and you can find it online, and it's really good at this kind of stuff. So hopefully that made sense. And that's the end of the question.